Hello friends, we'll be continuing with the chapter Permutation and Combination today, and we will learn some typical problems in permutation and combination. So we'll be doing some typical type of problems and how to solve them. So we'll begin with first type of problem, that is we'll call it TCP1. That is typical problem set is say typical problem, TP will say TP1. That is a typical problem set number 1. That is, they contains the problem type when you have to include P objects in a selection. That is, you are given a set of n elements, you have to choose r elements, but you have to choose these p elements for sure. Okay? So, what is the basic scenario remaining in this question? That is, you have to choose this r element, but in them p are fixed. But obviously, when you have to, we can't choose repeatedly the same element. So, if you had already chosen these p elements, so the remaining are n minus p. So, the remaining scenario is you have n minus p objects and you have to choose r minus p objects. Initially you had n objects and you had to choose r objects such that p objects must be there. These p objects must be there. So the scenario gets converted into this. You have n minus p objects and you have to choose r minus p objects. So as you can figure out, this is simple n minus p upon c r minus p. This is the first type of problem. So if you want to do a question on it, say you are given 10 elements, 10 objects, and you have to choose three objects such that object 1 is always there. So this is basically same as you say you have removed this element from the object set. That is, you have now 9 objects and you are choosing 2 objects because O1 is always present. So this would be 10 minus p, that is 1, c r minus p, that is 3 minus 1. This is similar as 9 objects are there and you are choosing 2 objects. Okay. So this is typical problem 1. Let's do it. And there is another category, say typical problem 2. This is pretty much similar. Just the difference is when you have to exclude p objects in a selection. That is, you are given a set A1, A2 till An and you have to choose r objects from it such that a set of p elements, that is these p elements, you can't choose from them. You can't choose any of the elements from them. So this just, it's pretty much same as you are given n minus p set, a set of n minus p elements, and then you have to choose r objects from it. Because these are not present. These p, whether they be on the set or they don't be in the set, that doesn't make a difference. Because you are basically choosing, we are not allowed to choose from these p elements. So the basic set remaining with us is n minus p. So the answer would be n minus p, choose r. So this is some typical problem set, two typical problem set based on selection. So as you can see, similarly this could have been, you don't have to choose. This could have been such that O1 is not present. So in that case, O1 is not present means you don't have to select this. So ideally you are having 9 elements and you have to choose 3. That is n minus 1 upon CR. Okay. So these are the two typical categories for selection. That is, when you have to include, you have to certainly include the P elements in the selection. When you have to certainly exclude those P elements from the selection. This is n minus P C R minus P, and this is n minus P C R. So similarly, there could be two typical problems sets corresponding to permutation. That is, you have to permute n elements taken R at a time such that P objects must be included. Similarly, here it could be you have to permute n elements taken R at a time such that P objects are always excluded. So that would be our typical problem 3 and typical problem 4. These are based on selection, so these are based on combination. That would be based on permutations, because you are arranging those elements. So our typical problem 3 becomes permutation of n elements taken R at a time such that P elements are always included. As we did in the previous lecture, when we were deriving the formula for combination, that is NCR, what we did was basically to find a permutation. You are basically first choosing R elements and then making the different combinations of it, different permutations of it. That is, you don't directly just start making permutation of R numbers. You just first choose R elements from the given set of n elements, and then you start making different permutations of it. This is an easier way to figure out how the different permutations will look like. So in this case, you can just analyze this by using that scenario only. First you have to choose R elements and then form the permutations of it. So to first choose the R elements when P elements must be there, means you have to use a typical problem set 1. That is, you are basically having n minus P elements and you have to choose R minus P elements because P elements will be there. Now, by choosing these R minus P elements, and you obviously had these P elements already, so R minus P plus P forms the basic R element which you needed. Now you have got these R elements, so you are having these A1, A2, this AR. You have to form one combination like this. Now you have to permute them to find a total number of permutations. So permutation doesn't depend on which the numbers they are. So this would be obviously arbitrary. It doesn't depend. You have chosen. You are given the R P to be fixed. You are already given that you have to choose these P elements, or you have just chosen by yourself. It doesn't depend on that. You are given R elements, so the total number of permutations corresponding to them would be R factorial. So total number of this would be into R factorial. So the total number of permutations of n elements taken R at a time such that P elements are always included is n minus P C R minus P into R factorial. So this is our typical problem set number 3. So similar to it would be similar to the typical problem 2. So this you can figure out that this is directly based on typical problem number 1. This is just by arranging them into R factorial ways. Another typical problem set 4 is based on the typical problem number 2, that is permutation of n elements taken R at a time such that P elements are always excluded. So what is the scenario now? You are basically having n elements, out of which p you don't have to use. So the remaining would be n minus p elements. Now you have to choose r of them. So you would choose in n minus p c r. Now you have got a set of r elements. So obviously you can form the permutations corresponding to each and every these such combinations in r factorial ways. So the formula for permutation of n elements, taken r at a time such that p elements are always excluded, will be directly based on tp2, that is n minus p c r into r factorial, because you can form r factorial corresponding to each and every combination you will get by using this formula. So this is a typical problem set number 4. So the examples you can say is, if I say you had 3 objects, choose 2 objects, 3 objects for say A, B, C, such that A is always there. Okay? So this would be basically, you had A fixed, you can either choose B or you would choose C. So there are only 2 ways. So this you will have figured it from here as well. That is total, there were 3. Now you have fixed one. So ideally you have just 2 elements to choose from, and you had to choose 2 elements, but now you have ideally 1 element to choose because 1 has already been fixed. So this would be 2C1. That is 2 ways. So this is what we got from the enumerating case as well. Similarly, if 1 element has to be excluded, the similar question when A was to be excluded. So the only 2 remaining elements would be BC. So one combination that would be possible is BC. So same would be what we would get from here. So we have to choose n minus p, that is 1 element has to be excluded, 3 minus 1. You have to choose 2 elements, that is 2C2 into r factorial, that is 2 factorial. You have to form the permutations as well. So you would have multiplied with this. This could be BA as well, this could be CA as well. So it would be multiplied with r factorial, that is 2 factorial into 2. So this would give us 4 over here. Similarly, it would be CB over here as well, BC and CB. So this would be 1 into 2 factorial, that is 2. So this is the basic problem set TP3, TP4. So number of ways to permute n elements taken r at a time where p are excluded or included. So we'll do another typical problem set. When you are basically given that scenario where you have to keep some elements intact with you. That is, you can't change their configuration. If I say there are 5 students such that they want to sit together in a row. If I say there were 5 very good friends who didn't want to part in a row, in a permutation. They wanted to sit together. So if I say, so this is our typical problem set number 5. Permutation of n elements taken r at a time such that p elements stick together. Okay? So basically what we are doing is, first of all, these we'll not choose R first. We'll try to understand the basic case. That is permutation of L elements taken all at a time, okay, such that 3 elements stick together. What do we mean by this scenario? So if you had say A1, A2, A3 till An, this was the say n elements, and if I say these three elements want to stay together, they don't want to part. A1, A2, A3 wants to be together. That is, these three would be close by to each other. They don't want anyone in between them. Okay. So if I say you just consider this as one block. If I say you consider it at B. Okay. You just consider it as a different element. Say B. Okay. So now the current set you will get is B. A1, A4, A5, A6, this continues then again. So this is the set you get. And how many elements are there in this set is, first you had n elements, you just boiled down 3 to 1. So you subtracted 3 from them and you added one element, that was B. So this is n minus 2 elements. So in general, if you boil down these p elements which wanted to stick together, you would get as n minus p plus 1. These are the total number of elements that are present in the new set. So you have to now arrange all of these. Okay? Because you have to find permutation of all these elements. So in how many ways can you arrange this n minus p plus 1 elements? This is obviously n minus p plus 1 factorial. Okay? And as you know, in this, all these permutations, you would have a place for B. Let us suppose A5, this was, say, one of the permutations out of them. Say this was one of the permutations out of them, these n minus p plus 1 permutations. If I say, now I again deconstruct this element B. So this could be deconstructed in such a way, A4, A5, this could be A1, A2, A3, A6 till AN, or this could have been similarly like this, A4, A5, this deconstructed block could be A2, A1, A3, because in this case also these all three are together, there is no one in between them. And similarly you can write another combination, that is A1, A3, A2. That is corresponding to any such configuration that you got in the permutation. You can permute these three elements again to form multiple permutations corresponding to them. So for each permutation that you got, by treating them one element, you can get p factorial permutations corresponding to each of them. So the total number of permutations would be this multiplied by p factorial. So this is our TCP 5. That is the total number of permutations of n elements where p elements want to stick together. That is, you just treat them as one block. So by treating them one block, you would subtract p elements out of this given set and add one set, that is the combined block of them. So this would give us n minus p plus 1 factorial ways to permute them. And now for each of the permutations you get, you can form p factorial permutation corresponding to the rearrangement of these p elements that was stuck into a united one element, that was B. So you can get for each of them p factorial. So you would get p factorial into n minus p plus 1 factorial ways to find a total number of permutations of n elements such that all of them are taken and p wants to stick together. So you can do it like this. If I say there, for an example, there were three friends, let us suppose A, B, C, and A and B wanted to stick together. Okay, so the total number of ways could be AB, C, another could be BA, C, okay, third could be CAB, and the fourth could be CBA. These are the only four ways in which this could have happened. So similarly, just when you derive it from the formula, that is how many elements want to stay together? There are 2, so there would be 2 factorial into n was 3 because there were 3 elements, minus 3, that were 2 elements, plus 1 factorial. That is 2 factorial into 2 factorial. That is equal to 4. That is what we get by just enumerating that. So this is the basic formula for finding the permutations where p elements want to stick together. So we'll do one more typical problem set, and that will be all for this class. This would be opposite of what we did right now. That is, you have to arrange, you have to find the permutation of n elements such that p elements never want to stay together. They want to be separated. That is, they never want any one of them to be together. They want them just to be separated. Okay? Given n elements, number of permutations. I'll see 1 second. Number of permutations such that p objects are always separated. Okay, so always separated. What does that mean? If I say A and B wants to be separated, there would be certainly a person who is in between them. Okay? If I say ABC wants to be separated, there would be certainly a person between A and B and B and C. There can't be a scenario where AB are together and there is someone between C. This is also not acceptable. So there would be certain person in between them. So in this case, basically, you can choose this in a way such that let us say you had n minus p elements. Okay, so these were the p elements that wanted to be separated. So there are n minus p elements, other elements, okay, which doesn't hold any such property. Okay, so you just place these n minus p blocks. N minus p blocks. Okay. Now I am saying is to place these p elements which want to be separated. These are the places for n minus p other elements, the n minus p block. For these p elements that want to be separated, I say either they can be over here, 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 similarly like this. They can be in between any of these elements. Okay, because whenever any of the element is in between over here, the next in these places in between them only one element can be there. So no two elements would be in any scenario together, because one would be here, one would be here. There would be certainly an element over here that is in between, or it can't be present over, say it is present over. So there are two elements in between. So n minus p blocks are directly there which can be placed. N minus p other elements can be placed in these blocks, and these p elements can be placed in between them. Okay, so how many positions are there in between them? You can say by whenever you had say two elements, there is one position between them. Okay, similarly you continue like this. There is one in the starting, one in the end. Okay, so the total number of positions available for them is n minus p plus 1. Okay. There are n minus p plus 1 positions for these p elements to be placed. So in how many ways can you place these p elements? That is obviously n minus p plus 1 choose p. Okay, in this way you chose the positions where to place. In which position, say you chose this position, you chose this position, you chose this position, you chose this position. So these are n minus p plus 1, they were the total number of places, you chose p of them. Okay, now you can permute these p, because you can change these positions. You have just fixed, yes, I will put one over here, one over here, one over here, one over here. You can interchange their position obviously, because that would change the total of the arrangement of these numbers, but that won't change the property that they are separated, because you have already fixed the positions and you have set the position in certain way that they will always be separated. So this would be n minus 1, n minus p plus 1 choose p into p factorial. Similarly, you can arrange these n minus p numbers also in these blocks, because you can change their arrangement to form new and new permutations. So this would be n minus p factorial. So this is our typical problem number 6. That is, when you want certain elements to be always separated, okay, then this is n minus 1, n minus p plus 1 choose p. That is, you are choosing, first of all you are arranging those n minus 1, n minus p elements that weren't supposed, there were no condition on them, you are just fixing them. You have chosen the places in between them that are n minus p plus 1 places. You have to choose p of them to place these p objects that want to be separated, and those you can permute in p factorial ways, and the remaining you can permute in n minus p factorial ways. So this is the basically typical problem number 6. So if I say there were 6 friends, say if there were 4 friends and 2 always, there were say 3 friends, 2 always wanted to be separated. So they were say A, B, C, and A and C always wanted to be separated. So in how many ways can you do it? You can either do it A, B, C, or you can do it C, A, B, A. There are only 2 ways. And if you try to think in the way we did, that is, you chose the element which you don't want to fix. That is B. You have no condition over it. You chose the position of B. Okay? In how many elements you have to choose? Places for 2, and how many places are there? 1 and 2. So from these 2 places you have to choose 2 places. That is 2C2, and those 2 elements you can permute in 2 factorial ways, and this element you can permute in 1 factorial way, because there is no overlap. This would be 1 into 2 into 1. That is 2 elements. There are only 2 possible ways in which you can arrange 3 friends such that 2 friends are always separate. So in this lecture we learned basic 6 type of problems on combination and permutation. First were based on some certain elements were always included in the set, how many ways we can choose them. The second was in how many ways we can choose certain elements such that few elements are always excluded. The third part was in how many ways can you permute certain elements such that few are always included. The fourth was in how many ways can you can permute certain elements such that some are always excluded. The fifth and sixth were something different, that were based on certain elements always being together, how many ways you can permute these total number of elements. And the sixth was in how many ways can you permute certain elements such that few never want to be together with each other. So these are the typical scenarios in which you get in the case of permutation and combinations. There are certain more kinds of problems we will discuss in the next lecture. There are typical problem set, more of typical problem sets. And then we will do some tough questions based on these, so that you get into the habit of solving permutation and combination. Thank you.